Hi folks, today we're looking at quadratic trig problems. As always, there are notes in the video description below, and there's also a link to a worksheet that you can do afterwards. So, what could be better than combining every high school algebra student's two favorite subjects, trig equations and quadratic equations? Not funny. But wait, they're not so bad, because you already know how to deal with quadratics. So here's the basic approach for quadratic. Make one side 0, factor, and then solve the little equations that come out of that. You could conceivably have ones where you had to use quadratic formula as well, but we're going to restrict ourselves to equations that we can factor. So what I'm talking about is an equation like this one. 2 sine squared x plus sine x equals 1. Okay, so the very first thing is we recognize it as a quadratic because there's something squared. Quadratic. We'll better deal with that. And our first step in terms of solving a quadratic is to make one side 0. So move that 1 over. Now we have to factor. This is really the same as having an expression like this. 2y squared plus y minus 1 equals 0. Okay? So we need to be able to factor that. And if you're not sure how to factor that, then you need to check that out, either by decomposition or by the box method or magic X or something that's going to work for you. But this factors into 2y, and we'll have y plus 1. And y minus 1. And you can check that out. By foiling, it's going to give you exactly what you had before. Well, if that's true, then we should be able to factor our trig expression. Instead of y's, we just had sine x's. So the first had to turn into 2 sine squared, so we'd have 2 sine x times sine x. And we're going to need our last terms to multiply to negative 1. One of these is going to have to be positive, the other one negative. If we botch which is which, we can always just try it again. And let me just check. I'm going to erase this once I'm done with it. But check, that would give me 2 sine squared x plus 2 sine x minus a sine x minus 1. Or 2 sine squared x plus sine x minus 1. Hey, that's what we started with. So we must have factored it properly. Okay, now that we have that, we have two little elementary equations that we can make. So the first one is that 2 sine x minus 1 equals 0. The other one is that sine x plus 1 equals 0. And notice here we're only solving for the first revolution. Okay, for each of these I'm going to need to rearrange them. So I'll move that 1 over and divide by 2. I'll have sine x equals a half. And this one over here, I'll have sine x equals negative 1. I factored, and I started to solve each of the elementary equations. That's all the new stuff that we're doing. And really, it's not new, because we've factored quadratics before in our high school algebra careers. All right. Now, we just need to solve each of these. We're doing it in radians, and it's the same method that I would have had before. Theta ref. Where is sine x a half? We've solved this a bunch of times. We know that it's at pi over 6. Okay. Sine is positive in these quadrants. And I combined steps 2 and 3 there. I knew that it was going to be positive in A and S. So that's 2 and 3 all together. And as answers, I'd have pi over 6. And I'd have this other one over here, which would be pi minus pi over 6. Or 5 pi over 6. Those are solutions in the first revolution that come from this elementary equation. Now let's deal with this elementary equation. We're looking for theta ref when sine is 1. That is 90 degrees or pi over 2. Okay, so theta ref is pi over 2. ASTC, sine is negative in these two quadrants. And here, I'll just be sure that I draw this carefully. Pi over 2 is 90 degrees. So 90 degrees in quadrant 3 and 90 degrees in quadrant 4 actually converge on the same spot. And the measure of that angle would be pi plus another pi over 2. Okay, so pi plus pi over 2, which makes 3 pi over 2, or 270 degrees. These are all solutions to the equation. Okay? And if we were to put them as a set, the solution set would be pi over 6, 5 pi over 6, and 3 pi over 2 in that first revolution. Now you might say, well, that's a lot of work. Well, it's about twice as much work as doing one of the regular equations, and that's because you have to do 2 of the regular equations. Aside from that, it's just factoring, which is pretty straightforward for us. Okay? And again, if you're not sure how to factor a trinomial or how to do difference of squares or common factor, you need to check that out. Let's try another one. Cos squared x equals cos x in radians for all x. So in the end, we're going to want general solutions here. Again, I recognize that it's quadratic because it's got something squared. That means I need to make one side 0. I can't just divide out by cos x because I may lose solutions. So cos squared x minus cos x equals 0. Now we'll do our first kind of factoring we always look for. GCF, or greatest common factor. If I take cos x out as a common factor, that's going to give me my 2 elementary equations. Okay? The first of which is that cos x could be equal to 0. And the second is that cos x minus 1 might be equal to 0. Or cos x equals 1. And now I'll just deal with these separately. Okay? Cos x equals 0. Reference angle of 90 or pi over 2. Now, it's 0. I think of that as positive 0. There are other ways you can deal with the poles, the zeros, the ones, and negative ones, especially if you know the unit circle. But this is going to work fine as well. So I think of that as a positive 0. I'm going to be in these 2 quadrants. Let's draw. So in quadrant 1, an angle of pi over 2 looks like this. In quadrant 4, an angle of pi over 2 looks like this. So our answers are going to be, the first one is just pi over 2. I want a general solution. The next one, I'd think of this as pi plus another pi over 2, or 3 pi over 2, plus 2 pi n. Okay, those are some of the solutions. Let's find the rest. Cos x equals 1. Let's find theta ref. Oh, cosine is 1 at 0. So theta ref is 0. Okay, and that's dealing with a positive cosine. So we're talking about quadrants 1 and 4. Let's go and sketch it. If I'm in quadrant 1 and I make an angle of 0, there I am. If I'm in quadrant 4 and I make an angle of 0, there I am. So that means that I'm at an angle of 0. That's my one solution for this. Plus 2 pi n, so it recurs. Now that doesn't look all that nice. Why don't we just write it a little bit prettier? We don't tend to write 0 plus. So we'll just call this 2 pi n. And this, and this, and this, that's my entire solution. Those ones on the left, there'd be a way to put them together more elegantly, but it's fine like this as well. Okay, let's do one more. Sine squared plus 6 sine x plus 5 equals 0. So again, quadratic because something is squared. In this one, they've been nice. They've already put it in equals 0 form for us. And you might be thinking, well, how do I factor it? So it's the same as y squared plus 6y plus 5. That's a short trinomial. So you're looking for numbers that multiply to 5 and add to 6. Two numbers that do that are 1 and 5. So this factors as y plus 1, y plus 5. If that's how it works with y's, then all we've got over here in place of y is sine. So we can factor this into sine x plus 1, sine x plus 5 equals 0. Each of those gives an elementary equation. So that means sine x plus 1 equals 0. Or sine x equals negative 1. The other elementary equation we get is sine x plus 5 equals 0. Or sine x equals negative 5. Let's go ahead and solve each of these. So number 1, theta ref. If sine is negative 1, let's see, where's sine 1? Oh, that's at pi over 2. Sine is negative for us in quadrants 3 and 4. Let's go ahead and sketch it. So we'd have quadrants 3 and 4 and a reference angle of pi over 2. So in quadrant 3, it would look like this. Pi over 2 is 90 degrees. In quadrant 4, it's going to look the same. Okay. So whether you think of it as pi plus another pi over 2, or whether you think of it as 2 pi minus a pi over 2, your solution is going to be the same. It'll be 3 pi over 2 plus 2 pi n, where n is an integer. Okay. Now the other one, sine x equals negative 5. Let's find the reference angle. I go through my chart. Sine x is never negative 5. Okay, that's no problem. Let's try this. I'll just have to do inverse sine of 5. I'll throw that into my calculator. Come on, little calculator. You can do it. There we go. Inverse sine of 5. Let's see what it thinks of that. Oh, it does not like that. The thing is, you can't have a sine of 5. If that meant what it does with regular triangles, with right-angled triangles, that would be something with a hypotenuse of 1 and an opposite side of 5. You couldn't draw a triangle like this. This doesn't give any solutions. Okay. Sine x can't be equal to negative 5. Sine can only take values from negative 1 to positive 1 inclusive. So this part over here, this whole business, doesn't give us any solutions. There are no solutions that come from it. Our only solution that actually worked was this. So anytime you find a sine value that exceeds 1 or is less than negative 1, you'll have no solution. Same thing with cosine. Not the same thing with tangent, though. Tangent can be bigger than 1 or less than -1. So there we go. We've put quadratics and trig equations together, and they weren't so bad. Once again, the answer to this one is just this bit here. And also, there are practice questions that you can download. Just check the video description. See you soon.